Hello, in this quick tutorial, I'm going to be showing you guys the ins and outs and basic usage of Xschem, and also the basic characterization of some of these SKY130 devices in Xschem. So you can see here on screen, I have some of the basic keybinds that get used most often in Xschem. Most notable being Shift-I to insert a symbol. So if we run Shift-I here, we'll see that this menu here pops up. And we can go ahead and go to find the PDK directory. So to find the PDK, you can start from the current directory or from the home and just find where you have the PDK saved. And to access the basic devices, you're going to go into the libs.tech folder, into Xschem, and into the SKY130 FDPR. So here are all the basic devices. And for this video, we're just going to do a basic characterization of the 1v8 NFET, so this device right here. So we'll just click OK, and we'll drag it out into our schematic. Okay, now let's go ahead and for our basic characterization, what we're going to do is a basic VGS sweep with a constant VDS. So what we're going to want here is a voltage source between the gate and the source, and a voltage source between the drain and the source. So if we go to our home and we find the Xschem devices library, we can see here that we have a voltage source. And so we'll get one here, and you can see here, we'll use our keybinds, we'll hit C to clone it, and bring one over here. We'll use the W command to create some wires. And we'll use U to undo. Okay, so there we go. Now you can see we have V3 right here, which acts as our gate source voltage source, and we have V4, which acts as our drain source voltage source. Okay, cool. Now we need to create a SPICE script, and to do that, we're going to go and insert a new code block, which is right here. And we'll go ahead and set that down right here. Okay, so when you place down a new code block, the first thing that you're going to want to do is change the name just to whatever. In this case, we'll just call it SPICE. And the value, we're just going to encapsulate it in quotes and include a break line. And the first line that we're going to want to have is this line right here. So this line right here is absolutely necessary for every new schematic that you make. And you can see here that it includes a new library and then finds the path to the ngSpice SKY130 library. And this command is going to be slightly different for everyone because everyone stores their PDK in a different directory. But as long as you change this first part of the command to wherever your PDK is stored, and then include the libs.tech, ngSpice, and then SKY130.lib.spice, you'll be good to go. And this just makes sure that ngSpice inside of Xschem can find the devices that are referenced in the SKY130 PDK. Okay, after this, we're going to focus on our SPICE script that we want to run on the circuit here. And actually, I forgot one thing. We need to probably add a ground. Okay, so if you've read the ngSpice manual, then you already have a good grip. It's just like any other SPICE language. We're going to create a new control and an NC, and we want to make sure that at the end of the execution that we save all results. So we'll go ahead and do a .save all. So inside this command, inside of this control block, we're going to go ahead and run a DC analysis, right? Because we're going to do a VGS sweep to determine the drain current at a specific VGS, we want to hold VDS constant while sweeping VGS. So generally, for simulations like this, we keep VDS at VDD over 2. So in this case, that's going to be 0.9 volts. And for now, we'll just set VGS to 0. Okay, now that we have that set up, we're going to run a DC analysis on V3, the VGS voltage source, and we'll go from 0 to 3 volts in 0.01 volt increments. And once we have that, we're going to go ahead and plot the drain current. And to do this, if we look at our SPICE, or rather our schematic here, right, we can see that the drain net is hooked up to V4, And so obviously just basic KCL, we see, okay, the current through V4 has to be equal to the current through the drain of the device. So to plot the current at the drain of this MFET, NFET, then we'll just do I of V4. And this again is the quantity of the current through V4. And because the current is actually going to be negative because current flows towards ground, we'll just make it negative I V4. Okay, so once you have all that done, in your options, you're gonna want to make sure that you have SPICE netlist selected instead of Verilog or VHDL or any of the other options. Okay, and once you have that done, you're going to want to go ahead and click netlist, and then once you're ready to simulate, just click simulate. Okay, so now we can see here that the simulation is finished, and we have our drain current plot right here. And so the best way to interpret this is that the x-axis is the gate source voltage, and the y-axis is the drain current of the MOSFET. Okay, so obviously from this graph we can determine a few things, such as the transconductance, the on resistance, and I guess you could almost call it the on point of the MOSFET. So this is a rather important graph. So we know that the GM is the partial derivative of this graph, or just a slope, but in some cases. But actually ngSpice does the GM calculation for us. So if we want to figure out the calculated parameters of this MOSFET and the calculated values, then we can actually use the SPICE simulation to do that for us. So in order to find the name of the MOSFET, we will run display all, and this displays all of the devices in the net list. And you can see here the device right here is our transistor, our MOSFET rather. So what we can do is do display the at symbol and then the name of that transistor, which is Xschem1, SKY130, FD, PR, FET01V8. And this will display all of the computed values from the SPICE simulation. So there's obviously a lot of important values in here. Some of the most noted are obviously is a GM. You can see here we have a very small GM because it's a very small MOSFET with a width of 1 and a length of 0.15 micrometer. With an estimated voltage threshold of around 0.757 volts, an estimated saturation point of 0.433 volts, and some other calculations that help with obviously capacitance, resistance, and the physical size of the transistor based off of the parameters and the PDK's idea of how you would lay out that FET. Okay, cool. Now, let's say we want to run the same simulation but with a slightly larger MOSFET. So we can go ahead and X out of that simulation, and we can right-click after selecting the FET and hit Edit Attributes. And maybe we want to simulate a MOSFET with a width of, 20. A really large MOSFET for, an amplifier. Well, we can do that. We can save it and run the same simulation again. And take a look at the results and see how they differ. Okay, so now we can see here that the simulation is finished, and we have a new graph. And we can immediately note some major differences. Now we see that the y-axis, instead of going up to around 1.8 milliamps, goes up to around 18 milliamps. And you can notice actually that the slope of the line is a lot steeper. So once again, if we want to inspect some of the computed values of this MOSFET, we'll run the same command we'll display at the name of the device. And we can see here now the new transconductance is a little bit bigger. Okay, so now that we've shown the basics of simulation and creating schematics in Xschem, in the next video I'll show you guys how to go from a full schematic into a layout in KLayout.